This video is to show you how to work the energy conservation with a rubber band word problem number 1. Again, all of these worksheets will use energy in equals energy out. So I have a bungee cord. It's stretched across a frozen pond, okay, which the fact it's frozen tells me we're probably going to ignore friction, which it tells us down here. So we can ignore friction. It takes 300 newtons of force to stretch the spring 50 meters. So this is my force. We treat a rubber band like a spring, and this is how many meters it is. So that tells me I'm going to use F of the force of the spring is equal to the constant, spring constant, times how far I stretched it. So that means I do 300 equals K times my 50. So K equals 6. Now, then I pull the cord back again, 40 meters. I have now stored energy in the spring. So the only energy I have going in is my energy of the spring, which is 1/2 K delta X squared. I put the weight on it, but I don't need that right at the second. So the energy of the spring, U of the spring, is 1/2 K delta X. Now this X is different than this one. This one was just the distance that went with this force. I now am only going 40 meters. So that's equal to 1/2. My K is over here at 6 times my 40 squared. So I punch that in my calculator, so that's 3 times 40 squared. So the energy in the spring is equal to 4,800 joules. Energy is always joules. Since I'm ignoring friction, all of this energy is going to turn into kinetic energy. Well, we have a formula for kinetic energy. This isn't spinning, so I don't have to worry about rotational. It's just my kinetic energy, where is it here? There it is. And if there's no label, that is the formula for linear. So kinetic energy equals 1/2 mv squared. So my kinetic energy is 1/2 mv squared, which is 1/2. My mass is 125. And my v squared is what I need. I need my velocity. So this potential energy has to turn into kinetic because we're ignoring friction. So this is 48. I didn't leave myself room. So that means V, and you should be able to do that. I just solve for this and take the square root, and we'll use the positive. So that'd be 2 times 4,800 divided by 125. Then I take the square root of that, and it's 8.76. If you do some in-between and rounding, you may get something slightly different. After it leaves the rubber band, there's no friction, so the acceleration is 0. So now I go to our old friend x equals v naught t plus 1/2 at squared. But that's 0, so the distance I go is my velocity times the time, which is 3.5. And I used the whole, my rounding may be a little different, so that's 30.67. Oops. That's problem 1.